Begin, we'll have some closing observations on backpropagation, which you have already seen to be a very important topic, one of the pillars of AI. And we'll start logic. I understand you had a full course on logic with the theoretical foundations, lots of important observations there, but we'll take an AI view, okay, artificial intelligence view of logic, because logic also is another pillar of AI, especially predicate calculus, because predicate calculus is the basis for knowledge representation. And knowledge representation has always been extremely important, even in the era of deep learning. Knowledge representation is important because we take small language models, and the small language models are augmented for their power by using knowledge graphs. Okay, knowledge graphs are based on the predicate calculus. All okay, everything coming fine. Okay, so that is the reason for studying logic. And now we'll make a transition from neural network based connectionist AI to again symbolic AI. Okay, so this is the way we'll keep transiting from symbolic AI or programming based AI to data and machine learning based AI, which is mainly neural network based. Okay. Yeah. So we covered sigmoid neuron with its interesting properties, where sigmoid neuron is 1 by 1 plus e to the power minus net. Minus net is the net input arriving at the sigmoid neuron, dot product of weight vector and the input vector. And importantly, this gives me a probability distribution over two classes. The derivative is quite simple, output into 1 minus output. We also covered the softmax function. Softmax function is a generalization of the sigmoid function from two-class to multi-class problem. And the softmax function gives me a probability distribution over the classes. And in softmax function also, the derivative is interesting. The derivative of the output with respect to the neuron's own input is output into 1 minus output, just like sigmoid. But the derivative of the output with respect to another neuron's input is minus self output into other neurons output. Okay. So these are very interesting facts, and they help us formulate the weight change rule. Typically with softmax, since softmax gives me a probability distribution, and two probability distributions are compared, their difference is computed by means of what is called the cross entropy function. The cross entropy function is target value multiplied by log of the observed value, where target value, observed value, all are probability values, summed over all the neurons in the output layer and summed over all the data instances. Minus of this quantity is called the cross entropy function. Okay, so cross entropy function and softmax typically go together, and they give rise to a very nice learning rule, the weight change rule, which is learning rate into difference between target and observed output at the outermost layer and the input at the connection. So the derivative of the neuron does not figure. And when we do backpropagation, this difference between target and output multiplied by the station derivative, which is the derivative of the neuron, that gets accumulated and passed backward to the neuron, which we are considering for weight change for hidden layer neuron. That's why the algorithm is called backpropagation. What gets forward propagated is the input value, and what gets backpropagated is the delta value. Delta value is recursive. Okay, the delta values at the higher layer, next higher layer, get multiplied by the weights backward, and then we take the station derivative of the neuron whose weight we are interested in and multiply it. Okay, this is how the backpropagation happens. So this is the general backpropagation rule. The universal rule is change in weight is learning rate into the delta value at the destination neuron and the input coming from the source neuron. This is called the universal weight updating rule. Whatever with the algorithm, whatever with the architecture, this is the rule which operates. And the delta value is target minus output into station derivative for the outermost neuron. And summation of backpropagated delta into station derivative for the hidden layer neurons. Okay, so this will get more cemented in your understanding when you do the assignment this particular week, where you'll have to introduce a hidden layer and see the functioning of the network when the hidden layer is introduced. Many functions which are not computed by a single neuron or a single layer of softmax neuron are become computable when the hidden layer is introduced. But for the sake of what is called explainability these days or interpretability, you'll have to understand what is going on in the hidden layer neuron. For example, for XOR, you will have to find out if the hidden layer neurons are computing x1, x2 bar and x1 bar, x2, or are they computing OR of x1, x2 and NAND of x1, x2. Okay, so this you will have to observe. And the outermost neuron correspondingly will compute either OR or AND. Okay, this you will have to observe and show to the TAs, to me also. So as I've been saying, since the lab is sort of shadowing the theory, okay, lab and theory are going together. So that's proving to be quite convenient, at least for me. I understand where your understanding is. And it was nice for me to see that many of you are getting good convergence for weighted majority, but convergence is not happening for palindrome, which also even parity, because palindrome even parity, these from these the XOR and XNOR functions become special cases. So if these general functions were computable by a single neuron, then XOR XNOR also would be computable by a single neuron, which is not the case. So one thing though you'll have to remember, I saw a bit of lack of understanding there. You'll have to compute the loss per data instance. Okay, so the total accumulated loss divided by number of data points. For example, for 5 input palindrome, you have 32 data points. So per data instance, what is the loss? That I have asked quite a few groups. And you have given me the values there. Whereas for weighted majority, the per instance loss becomes almost zero. For palindrome, the per instance loss value is significant. 1.5, in some group it was 3.2. It depends on the initial value, right? And the learning rate and so on. So good, I think you're plotting the graph and seeing the loss behavior, which is instructive. Okay, so the hidden layer probing or investigation you will do in this week's lab. And after that, if you remember, next week will be your midsem, okay, lab midsem, where you will be given a question which you have not seen before, and you'll have to solve it within a span of about 2.5 hours. We also have seen that vanishing gradient, exploding gradient can happen in deep neural networks. Now, deep neural networks have many layers, many hidden layers. And as we have seen, the backpropagated delta is computed as follows. So here, the delta value is the delta value in O1 and O2 multiplied by the weights used backwards, summed up, and multiplied by the station derivative here. Okay. And as you go downwards towards the input layer, these station derivatives keep on getting multiplied. The derivatives are typically less than 1, between 0 and 1. So this cumulated multiplication leads to a very small delta value eventually. So, so this leads to what is called a vanishing gradient. And after a while, since the gradient is very small, because of the universal rule of weight change, the weight value will hardly change. None of its fault. The fault is in the technique. The technique is that of backpropagation and leading to multiplication of derivatives continuously, leading finally to weight change being almost zero. This is the vanishing gradient problem. Now, is this problem real? This problem is real. First of all, for non-trivial problems like weather prediction, stock market data prediction, depression detection, loan application sanctioning, visa application sanctioning, where classification is involved, you typically need many hidden layers because we have seen from the theory of segments, right? Regions leading to the capacity of the neural network. We have seen that more and more neurons have to be introduced for producing regions, for producing more and more hyperplanes and more regions. This you have seen, okay, and I have proved it also, capacity of the neural network. So you have to introduce more and more neurons, more and more hidden layers, so more and more vanishing gradient. Okay, this will happen for non-trivial problems. Another very interesting situation is where the neural network is used for sequence processing. Sequence processing appears in natural language processing, genome sequencing, where you have a sequence of elements and you have to make some decision with respect to each sequence. Sequence processing also happens for chatbots, okay, conversational AI. So how does it happen? Let's say you and I are carrying out a dialogue. I say something, then you say something, then I say something, then you say something. So continuously dialogue turns are accumulating and it becomes a long sequence. And suppose at the end of the sequence, you are required to understand what is the conversation outcome. Okay. For example, we had done a problem with I believe one of the large companies where the idea was to see if the conversation is leading to the sale finally or not. Okay, so the salesman is interacting with a customer. This dialogue is carrying on, and we have data of whether the dialogue succeeded in converting the conversation to an actual sale or not. So there were positive and negative examples. Conversation data which led to success, conversation data which finally failed. The sale did not happen. So now this is a case of sequence processing where you have to finally predict, is this conversation going anywhere? In real life also you see this, right? Say two friends are talking with a view to achieving something. And gradually both the parties begin to sense, is this negotiation leading to something fruitful or not? So this happens. So we want an AI agent to predict this. So this is a very interesting exercise. And what happens is that if when the sequence length increases, sequences, by the way, are processed by what is called RNN, recurrent neural networks. So a neural network looks at every element in the sequence and begins to accumulate the history and finally predict if the decision is yes or no. So this way of gradually building the network is called backpropagation over time. Okay, a feed-forward network emerges from a single network. Okay, you will do this in deep learning courses. Deep learning for NLP, for example, which I teach, where a recurrent neural network is unfolded over time. And the final decision appears in the final state of the neural network. Okay, and there, if the sequence is long, you can see that at every layer, at every stage, you have a hidden layer. Okay, a simulated hidden layer, not an actual hidden layer. The network replicates itself over time. And such a feed-forward network, which is simulating a recurrent network, has a lot of depth and it suffers very badly from vanishing gradient problem. So this problem is really real. Okay, it happens when you use neural networks for sequence processing. And vanishing gradient problem can be solved using ReLU, because ReLU has this interesting behavior. Up to 0, the derivative is 0. After that, the derivative is 1. So derivative is either 0 or 1. Therefore, the ReLU neuron either passes the backpropagated delta completely downwards or doesn't pass anything at all. Now, it is never the case that for very large neural networks in a layer, all neurons are passing 0 delta. No, not the case. Some of them pass the backward delta completely. Some don't. Okay. So eventually you have a result in the network, but you do not suffer from vanishing gradient problem. Vanishing gradient problem is also solved by what is called LSTM, long short-term memory. Again, a different topic in deep learning based sequence processing, and notably NLP, for example. Okay, so ReLU is also approximated by something called soft ReLU, which you should read up, and also I believe GELU, GELU. I forget the expansion for GELU. And then this becomes continuous, and the derivative exists even at the knee of the curve. Okay, so those are very nice and nitty-gritties, which you should know. So if your exercise is to read up on ReLU and the soft ReLU, and all the exercises that I have given coming out of the lectures. So now let me close backpropagation with some important concepts associated with feed-forward network and backpropagation. You know, backpropagation works by forward pass and backward pass. And then we know that linear neurons will not work. Nonlinearity is essential. And if you have this network where the H1 and H2 are computing y is equal to mx plus c, the output neuron also is computing y is equal to mx plus c, then you can simply apply a composition where H1 is a linear function of x1 and x2. Similarly, H2, y is a linear function of H1 and H2, and then apply composition and see that y is also a linear function of x1 and x2. So then you don't need the hidden layer at all. It is collapsible to one neuron with connections directly from x1 and x2. So this, before that, you have to prove that a linear neuron cannot compute XOR. Apply upper threshold, lower threshold, and set up the inequalities and see that the inequalities are inconsistent, just like in sigmoid. Okay. So I've given the inequalities, and you can see that it is inconsistent. Okay. Then there is this problem of local minimum. Backpropagation is greedy. So in the lab, some groups have pointed out that the error is increasing and then stabilizing. Okay, some of the groups have pointed out. So how can error increase? By theory, the error cannot increase at all. Gradient descent by nature is error decreasing always. So it's a greedy algorithm. So if the operating point is here, then by small steps, if the learning rate is small, it will gradually descend into M. And then it will never be able to come out. Okay. So to shake it out of the local minimum, you will have to reinitialize the network and hope that the operating point gets initialized to go somewhere here. And then gradually by small steps go to G, which is the global minimum. So this is a slow process. So back in 70s, 80s, another parameter was introduced. It is called the momentum factor. The momentum factor operates as follows. The change in weight at the nth iteration has two components. One component is due to gradient descent. The other component is called due to momentum factor. So beta is called the momentum factor, one of the parameters. Eta is the learning rate, and beta, the momentum factor, is typically 1/10, of eta. And the momentum component is beta into the last iteration's change in weight. So you take a proportion of the last iteration's change in weight and add it to the gradient descent component to get the change in weight at the nth iteration. Okay, so pay attention. The change in weight at the nth iteration is gradient descent component at that iteration plus a fraction of the previous iterations weight change. That fraction should not be too much. Okay, beta should be small compared to eta. How does it operate intuitively? If we are considering A, B, C, and then going into, let's say, M. So we want to move fast over the landscape where the gradient is not changing sign. So if I'm moving over the flat surface, I would like to move quickly. But near the minimum, if there is too much of oscillation, then that will slow down the convergence process. That reminds me, you will have to observe this behavior by introducing a momentum factor in the lab and see its effect. Okay, so do that. So what happens is that when I'm in this terrain, in this part, let's say I'm at B. So at B, the change in weight will be plus, positive, because the gradient itself is negative. Now, last time at A also, the change in weight was positive. I'll have to take a fraction of the change in weight at A and add it to B. And thereby, the effective weight change becomes larger. Okay, so the change in weight becomes larger than what gradient descent will dictate. So I'm taking a larger step. So the effect of momentum factor is to accelerate the movement when there is no change of sign in the gradient. But near the local minimum, let's say go from C to D and from D to E. At E, the change in weight will be gradient will tell me that the change in weight is positive. The previous change in weight was negative at D. And so two things get subtracted. So the effective change in weight at E is smaller. So that has a dampening effect. So the effect of momentum factor is to accelerate movement on a flat terrain and decelerate the movement near a local minimum. Okay, so that is the effect of momentum factor. Now, it will be interesting for you to see what happens if beta is large compared to eta. Then effectively, you will see that the change in weight at any point becomes a GP series, geometric progression series, and the gradient descent effect is nullified completely. It doesn't have any effect. Okay, so momentum factor also has lots of interesting consequences. Any question? Local minimum, global minimum, momentum factor. Another very interesting problem is symmetry breaking. Okay, so you take axon network and do observe it in the class. Even when you have introduced the hidden layer, suppose you initialize the weight values to equal value. Okay, all weights are equal. Then you will see that the network doesn't converge at all. Okay, what is the reason? Say all weight values are equal. So the input from here to both hidden layer neurons are same. Okay, and they have started with the same values on the weight. Now you have found out the difference from the target value at this neuron. Now what comes backward as delta value is also same for both these neurons. Okay, what comes back as delta value is also same for both these neurons. Now, since eta delta into the input is same for both these weights, their change also will be same. So if they started out same, it will never be possible that they will become different eventually, whatever be the input. Okay. Now the final convergence requires the weight values to be different, but they will never be different. So the network will not converge. Okay, so this is the consequence of symmetry. Now you need not make all weight values equal. Particular weight values have to be equal. So that can be understood by this diagram. So instead of placing x1 and x2 side by side, you place them vertically on the axis of symmetry for the XOR network. So place x1 here and then x2 here, and the weight values are on two sides of this axis. Now, the weight values on the two sides of the axis of symmetry should not be correspondingly equal. So these two weights should not be equal. These two weights should not be equal. These two weights should not be equal. If they are equal, okay, that means if the values of the two weights going from x1 to the hidden neurons are equal, similarly for x2, and similarly from h1 and h2 to the output neuron, the symmetry exists and the network will not converge. Okay, so this is the symmetry breaking problem. It was not understood initially. Okay, and when this observation came that the network is not converging in spite of having a hidden layer, many hidden layers, many neurons, why is it not converging still? It was traced that it is due to symmetry breaking problem. So symmetry breaking problem is general. If you keep this axis of symmetry in mind and let there be any number of hidden layers, just remember to place the neurons on the axis of symmetry and the corresponding weights on both sides. Then symmetry breaking is clear. Again, I would like to sort of request you that do attend the classes and look at the slides, hear the recordings, because many of these explanations are not well described, okay, in the textbook and research papers and so on. So in many cases, my derivations or explanations seem to be clearer. Okay, symmetry breaking, for example, this way, I have not seen an axis of symmetry, though it is implied. Okay, but actually drawing the axis of symmetry and placing the weights on two sides of this, I have not seen such a diagram. On the other hand, it is essential for understanding. Similarly, the derivation of softmax and cross entropy leading to weight change rule, which is independent of station derivative, that also I have not seen explicitly anywhere. Okay, so it will be good if you attend the lectures, look at the slides. Okay. Let's begin a very important topic coming from symbolic AI, okay, which is based on Turing machine symbols. So theory of CS, it is in two parts, theory A and theory B. Okay, so theory A deals with logic and theory B deals with algorithms and complexity, which are extremely well founded, the foundations of computer science itself. Theory A, logic, theory B, algorithms and complexity. From both sides, artificial intelligence has drawn material, and AI itself has also contributed to many of these things. So we start with basic concepts like axioms and rules. I understand that these have been done in a previous course, but that's okay. It doesn't harm to repeat some of these fundamental things. So some foundational questions for mechanization or automation of knowledge representation on reasoning. What are symbols and concepts? Okay, leading to what is called the well-formed formulae. What are the self-evident and ground truths in the system? They are called axioms. Okay, so for example, when we read geometry, there were 5 axioms of Euclid which we have seen before. Okay, these are self-evident. You cannot question them, and you are not supposed to prove them from more fundamental principles. You have to start from those. What is the validity of the inference? So when we start from those axioms and apply inference rules, what comes out of that process? What is their validity? Are they really true? So the notion of proof, notion of truth, they have to be discussed. They are again at the foundation for intelligence. Is the inference system powerful enough to capture reality? This is called completeness. Can it be implemented on a Turing machine? This is called derivability and complexity. So notice that all these are questions on computation, and we have to be falling back on Charles Turing hypothesis, which says that anything that is computable on a Turing machine, and anything that Turing machine computes is the only and all set of computable functions. Okay, so these are abstract. Let us begin to make them more concrete. So you have gone through Boolean algebra and propositional calculus. Though this comes at the elementary stage, their importance is paramount. First of all, propositions. Propositions stand for facts, assertions. They're also called declarative statements, as opposed to interrogative statements like questions, and imperative statements like request, order, etc. So from today, you begin to note how much of your conversation and how much of the statements that you make are declarative in nature. Okay, so I'll go for breakfast in the morning. It's a declarative statement. Will you come with me? That's an interrogative statement. Okay, please come with me for breakfast. That's a request. Okay, so there are these three kinds of basic statements, and propositions correspond to declarative statements. Grass is green, sky is blue, and we have a way of representing those pieces of information. Then there are operators and or not and implication. Okay. Implication and not form a minimal set, can express all other operations. So this you probably have seen. So not P implies Q. Okay, yeah, not P implies Q. P implies Q is equivalent to not P or Q. Okay, so not and implication can give rise to and operator and also or operator. Tautologies are formulae whose truth value is always T, whatever the assignment is. Tautologies. And then we have this very important notion of model. We use the word model all the time in machine learning. When we have trained a machine learning model with data, a machine learning system with data, we eventually get a model. Okay. In propositional calculus, model has a very specific meaning. Any formula with n propositions at 2 to the power n models. Okay, these are also called assignments. So tautologies evaluate to true for all models. So for example, P or not P is always true. And P can take two values, 0 or 1, false or true. So if P is false, then not P must be true. If P is true, not P must be false, and there or must be always true. Okay, so it's a tautology. Similarly, not of P and Q is equivalent to not P or not Q, the De Morgan's formula. This is also a tautology because if you put the values of P and Q, 0, 0, 0, 1, 1, 0, 1, 1, then this whole thing evaluates to true. So this is De Morgan with AND. So here is the truth table for not P and Q implies not P or Q, not P or not Q. So you see I have given the values of P and Q. There are 4 models here, 4 assignments, TT, TF, FT, FF. And not P and Q evaluates to F, T, T, T. And the right hand side, not P or not Q also evaluates to F, T, T, T. So with the result that L implies R evaluates to T for all rows, for all assignments. So it's a tautology. Now we introduce the notion of formal systems. Okay. Formal systems are rule governed. Okay, our hands are tied. Once we enter a formal system, okay, our hands are tied. Definite rules are given. Strict description of the structure and the rule application. Are there real life examples of formal system? Yes. The legal system, for example. Okay. So the legal system of India is based on Constitution of India. And when we operate in the legal system, our hands are really tied. The laws, rules, sub-rules, sub-clauses are all given, and we have to completely adhere to that. Okay. So one of the tenets of the legal system, for example, is not guilty until proven otherwise. So listen to this carefully. Not guilty until proven otherwise. Do you realize the importance of this rule? It is because of this rule that we are roaming around freely. We are not inside jail. Okay. It is presumed that all of us are not guilty of anything. Okay. So it comes by default unless proven otherwise. Until it is proven otherwise, we're free. Okay? Of course, obeying all the other rules. Constitution of India, we have to pay taxes. We should not steal anything. Right? So rule governed system, strict description of the structure and rule application. For example, the IIT's system is also a strict structure and there are definite rules. Students have to follow rules, faculty members have to follow rules. The constituents are symbols. Okay, a professor is a symbol, a student is a symbol. And then there are well-formed formulae. That means structures which are created out of these symbols. For example, this class is a well-formed formula. Okay, I have to sit here. You have to sit there. You cannot sit here. Okay, and you have to sit side by side. This structure is very rule governed. Okay, and also you cannot sit on the benches. You have to sit on the chairs. I cannot stand on this table and begin lecturing. See, so many rules, so many rules. Well, so this creates a well-formed formula, which is a structure. And then there are inference rules. So inference rules create new structures. Then there is an assignment of semantics, which takes us to AI. From a theoretical framework to artificial intelligence, which is practically applied. This is contingent on assignment of semantics. Then there is the notion of proof. Proof has a very strict meaning. Okay, proof is a very, very strictly defined notion. The notion of soundness, completeness, consistency, decidability, etc. This I'm sure you have been exposed to in the logic course, but we'll take a view from AI. So to concretize all these things, let's take up one of the most beautiful structures in theory, as a framework in theory, Hilbert's formalization of propositional calculus. Hilbert, okay, mathematician, his formalization of propositional calculus. Hilbert's formulation of propositional calculus, was it done in the logic course for you? Specifically Hilbert's formalization? No? No. Okay, so this is a beautiful exposition of what it means to formalize anything. What it means to formalize anything. So in Hilbert's formulation of propositional calculus, the elements are propositions and they are denoted by capital letters. Operator is only one, implication. Okay, only one operator, it's the implication. Then there is a special symbol F. It is called false. Its name is false. there are two other symbols, open parenthesis and closed parenthesis. Well-formed formulae are constructed according to a grammar. Well-formed formula is P, a proposition, or the symbol F, or WFF implies WFF. Okay, so well-formed formula means the following. It can be either a proposition or the false symbol, or created from earlier formed WFF, leading to more complex structures. There is only one inference rule. It is called modus ponens. If you are given A implies B and A, then you can infer B. You can write B. Okay, so these are the building blocks of propositional calculus as given by Hilbert. But now more interesting things are coming. The next building block is the set of axioms. These are starting structures. They are supposed to be taken on the face value. They need not be proved. So the first axiom A1 is A implies B implies A. A implies B implies A is the starting structure. The second starting structure is A implies B implies C. This whole LHS implies A implies B implies A implies C. And the final axiom A3 is A implies F implies F implies A. Okay, so two false implies the proposition itself. Now, it is amazing that these three axioms and only one inference rule, modus ponens, gives rise to the whole of Boolean algebra and propositional calculus. How did Hilbert come up with these axioms? Well, that's how genius operates. Okay, that's how genius operates. So A1, A2, and A3. Now let's see how these axioms and modus ponens is used. So we have to understand the notion of proof. But before that, let me exemplify the proof. Prove that P implies P is a theorem. Now, what is a theorem? A theorem is any structure that is proved from only the axioms and the inference rules. Okay, so prove that P implies P is a theorem. So, so we start this way. P implies P is instantiated from axiom 1. Axiom 1 is A implies B implies A. Also, P implies P implies P. Again, axiom 1 is applied, where B is P implies P and A is P. Here B is P. Now apply, introduce another, now use the second axiom, which is P implies 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 P. So this is A implies B implies C implies A implies B implies A implies C. Okay, with P for A and P implies P for B and P for C. Now apply modus ponens on 2 and 3 and you get P implies P implies P implies P implies P. Now apply modus ponens on 1 and 4 and get P implies P. So this proves that P implies P is a theorem because you applied only axioms and the inference rule. You remained within the system. Okay, you remained within the system and created this structure. So this structure is called a theorem. So from theorem come the notion of tautology, soundness, completeness, and so on. So it turns out that any theorem of propositional calculus is provable within the system. Okay, using the axioms and the inference rule. Let me end the class with with the AI notion, which is of about confusion inside the system, outside the system. So theorems which are proved from the axioms and the inference rules are within the structure. Now the question is, can everything be proved? Okay, not everything can be proved if the system is powerful enough. Okay, so that leads to what is called Gödel's theorem. In real life also we have things which cannot be proved. For example, the truth of this statement cannot be established. This statement is false. So this is a self-referential situation. This statement is false. Can you decide if this statement is true or false? You cannot. If you say this statement is true, then you have to infer that this statement is false because it is saying this. And if you say no, this statement is false, then you are agreeing and the whole statement becomes true. So this arises from what is called the self-reference problem, the of and about confusion. Truth or falsity cannot be decided. Another example is this, you probably know, a very famous example. A city has a barber who shaves all and only those who do not shave themselves. A city has a barber who shaves all and only those who do not shave themselves. Now you cannot answer this question. Does the barber shave himself? If the barber shaves himself, then he cannot shave himself. If the barber does not shave himself, he has to shave himself. Okay, because of the starting proposition. So there are statements in real life also whose truth and falsity cannot be determined by the very nature of self-reference. Okay, so more about it as we go forward. What is the importance of this in AI? The importance of this in AI is that there was a program in 1930s, an ambitious program. Bertrand Russell, I think, was one of the proponents of this, that whole of mathematical knowledge can be derived automatically from starting axioms and inference rules. Okay, whole mathematics can be churned out from an automatic machine. Then came Gödel's theorem in 1930, saying that there are structures which are constructible from within the system, but which are not provable by the system. Okay, so the Gödel's incompleteness theorem, and that put a stopper to this program for automatically creating whole maths out of a set of axioms and inference rules. Okay, so we'll deal with these very interesting questions, and the assignment will be on you'll have to implement something using Prolog. Prolog will be covered in the class. Okay.